So you're going to find out in PLC that a lot of the terms that we use with computers, you've also got to learn for program controllers, because they are computers, and they came out through computers. The first basically programmable controller I ran into was strictly a computer. It was a DEC computer, and it ran number 8 blast furnace out at USB. But they adapted it over, so it programmed in standard languages like that was around then, like Fortran and stuff like that, which was a text-based language. So, describe the invention and the development of history of programmable logic control. Discuss the benefits of PLCs over electromechanical relay systems. Distinguish between fixed and modular PLCs. So the 1100 is technically a modular PLC. I called it a hybrid PLC, but we do have some 500s, 504s over in where we used to teach the class. Those things are way too big for me to bring over together. Discuss the difference between Intel and Motorola microprocessors, which is okay. We need to know the difference between RAM, random access memory. We need to know the different type of ROM. And of course, we've added a new type of memory that's very popular in PLCs. Which we call flash memory. This is the same type of memory that's inside your thumb drive. Explain the use of address decoder circuits in the PLC. List the major components of a PLC power supply. Describe Allen Bradley programming controller devices. All devices have discrete, which is, the book uses discrete a lot. And what they're talking about is that these are inputs or outputs that only give us 2 states. It looks at a voltage level, by the way. A lot of times in digital, we represent ones and zeros. So we have to be able to represent ones and zeros. And we've only got 3 electrical quantities we can use. What's the 3 electrical quantities? We're not talking about power. What's 3 electrical quantities that you deal with all the time? One of them starts with Z. The 3 electrical quantities. One of them starts with V. Volts. Not watts. Watts is the result of 2 quantities. Volt, current, resistance, or opposition. Which of the 2 can I send stuff with? Current and volts. We can't send resistance, right? You understand that? It's there, right? So that means so most digital signals are represented with either current or voltage. Here we're primarily using voltage. So on our input ports, these are DC. If I put 24 volts on that input port, it's considered to be a 1. And of course, a 0 volts is considered to be a what? A 0. Now that's true most of the time, but not all the time, because all we're doing is looking for 2 states. There's some signals that don't do that. So I know of one that a positive voltage is actually a 0 and a negative voltage is actually a 1. All we're doing is looking at 2 different states, right? And if it generates an output, ours is gonna output 24 volts to represent a 1 and 0 volts to represent a 0. And the book calls that discrete. A lot of people call that binary. So binary is a number system that only has 2 states, only has 2 digits, 0 and 1, or digital. Most of your U systems. So we have a method. Y'all take algebra. One of the main things you do in algebra is learn how to take a big equation and do what? Reduce it. We have an algebra we learn, you'll learn a little bit in digital, not in great detail because we don't do design, but it's called Boolean algebra, B-O-O-L-E-A-N. So most of your computers, so Siemens and Allen Bradley refer to binary information as Boo. Then we have what we call analog inputs. The Micrologic 1000 doesn't have the analog inputs, but the Allen Bradley PLC does. This 1100 unfortunately, we don't live in that type of world, right? So temperature is not food, right? It's not one temperature varies over a great range of light representative. You know, the sun don't pop up to the sky and go down at night, right? You understand? You got all these different variables. So we live in an analog world, but originally PLCs were digital. That's all they dealt with digital. They realized sooner or later that they had to come up with a method where we can take a digital or an analog input, which is constant variable, and convert it over to a binary number, not just one to zero, but an actual binary number that represents that. So most of your PLCs now deal with analog. The 314, the ones that's running the Amatro line, it has analog inputs and analog outputs. So not only can it generate read a number of voltage level between a certain level, right? You understand it can also generate it. So a lot of your variable frequency drives that we control the speed of AC motors deals on an analog input. So we'll send in an analog input, and that would cause the motor to run at a certain speed. So analog and digital. So the book's going to call it discrete. I'll probably call it binary. So it's either there or not there. It's either on or off. It's either true or false. Where analog can vary, you know, all kind of ways. Are we okay? That makes sense? So the little thing, the security checks when you come in, your temperature is analog, but that computer that's running that thing has the ability to take that analog information and display the digital number, right, to represent that. So this is the basic block diagram of a computer. We have a central processing unit. Of course, we got to have a power supply. And this is normally DC, guys. Then we're going to have inputs and output modules that connects to the PLC. Oh, that's analog. And then what the book calls what? What the book is going to refer to as discrete. Input, you know. That makes sense? Okay? So, we have two types of PLCs. So, but that, you can't expand it. Everybody okay? This is a modular PLC. This is the old way, and they're still available, guys. You can still buy fully modular PLC. A modular PLC, and this is a trainer, but a modular PLC has a rack. So this is the rack, and then it has what we call a backplane. This carries all the power and addressing information from the CPU module to all the other modules. So this would be what we call a 7-slot rack. One of your slots are going to be occupied by the CPU module. But everything's done in modules. What's nice about this is you get what you want, right? You understand? So you decide how many inputs you need, you decide how many outputs you need, you decide how many analogs you need, all this other kind of stuff. It's up to you. And then you can buy another module that fits on this guy that allows you to connect it to another rack. That other rack wouldn't have a CPU in it. So this is a truly modular PLC. So what's the advantage of this? Well, you can keep, of course I don't have it anymore, but I had a computer at my house that looked the same for about 20 years, but it was always different because I didn't buy like this. I bought a chassis computer, and I could change motherboards out, I could change video cards out, so I could keep that thing upgraded exactly what I needed when I needed it, right? You understand? So people walk in and say, you still got that computer? But it wouldn't be the same computer because I knew I bought it to be, I could upgrade it, right? You understand? Most of your laptops you buy now are fixed, right? You what? You get what you pay for. Most of your cell phones are fixed. You get what you pay for. If you want a better camera, what do you have to do? Buy another one. If you need more memory, what do you have to do? Buy another one, right? And so that's basically what a fixed PLC is. You get what you pay for. If you want more, you have to scrap what you got and go out and buy a new one. A modular, you can change the CPU out. So as long as it meets this rack, so all of a sudden they come out with a new CPU. Change it out. If it's still compatible with your modules, you got no problem, right? Odds are it is. So the advantage of a modular PLC is that you can keep it watch, you can upgrade it constantly, and you get what you want. So if you buy a fixed PLC, it's going to come with a certain amount of inputs, it's going to come with a certain amount of outputs, and when you run out, you're screwed, right? You understand that? So I think ours has 10 inputs and 6 outputs. I think that's what the 1000 has, the MicroLogic 1000. Well, if you needed 11 inputs and you didn't plan ahead, right? You understand? You got problems. What they've gone to now, so that's a modular PLC. So it's got a rack, right? By the way, we still call it a rack even though it's not true. It's got what we call a backplane. The backplane carries address and information to select the different modules, and it also carries power down through there. The first slot, we call it slot 0. It's usually on the left, and this is where the CPU module goes. And then after that, it's up to you what comes in slot. It's up to you to buy slot 1, slot 2, slot 3. So Allen Bradley has modules that have up to 32 inputs on a single module. We got 16 inputs on ours. This is the type PLC that's become very, very popular. They still refer to this as a modular PLC. I call it a hybrid PLC. So this is the actual 1100. So this is MicroLogic 1100. And then it's got a panel on the side that you can snap off and you can add multiple modules. So the backplane actually runs through the microprocessor and through the module. Everybody understand that? Makes sense? We'll show y'all Siemens. So here, this guy you can add up to 4, MicroLogic 1100, you can add up to 4 additional logic modules. So if you run out of modules, but you got all types of modules you can buy for this. I call it a hybrid because it's got some fixed inputs, it's got some fixed outputs. So ours has 10 inputs inside the PLC. It's got 6 outputs inside the box, and then if we want to, we can expand it. It don't physically have a rack. They mount on what we call a DIN rail. And this is pretty small. And we'll show you how we can. So they just snap on, snap off. It's real easy to. Get my cord from. And that's our Snap-on toolbar. So this is what we got. We got this guy right here. So you can use it as a fixed PLC, but if you need to, you can do what? You can add on more. So PLC, central processing unit, of course, a microprocessor is usually a microprocessor. When I first worked, the first computers I ever worked on was what we called it was a desktop. It wasn't a desktop. It was a mini PLC. We called it a mini PLC, not a PLC. We called it a mini computer, but it was actually a desk, and the actual CPU was made up of like 3 different circuit cards. Then they came out with what we call the microprocessor, where they took everything that was in that one circuit card, and they integrated it onto a single chip. And that became known as a microprocessor instead of a central processor. What we do on the PLC, though, is on the PLC, all of this is considered to be what we refer to as the CPU. So that's kind of different. So all your input ports, all your output ports, all this that makes up, so this is the actual ports here. So the ports are actually outside of what we call the CPU. So when you select the CPU, you're specifying how much ROM it's got in it, how much RAM it's got in it, what type of processor it actually runs, so it knows the machine language. And all this would be what we refer to as the CPU. So we call this, and I call this the 1100 CPU. So it's not quite what the CPU actually is, but that's what it's referred to. So, make sense? So the microprocessor is actually the brains of the computer. And I have problems with that. Computers can do one thing. Anybody know that one thing computers can do? So that microprocessor can do one thing. Anybody know what that is? It can run a program. And who writes programs? People. So who's the brains of the computer? Not the processor. It's the people that write the programs that the computer runs. So all the computer does, all that microprocessor does is one thing, it runs programs. All it knows is when you tell it, it goes to a certain location in memory when you turn it on and looks for the first instruction. Then after that, it's slave to the program. So, but people call it the brains of the computer. But all it can do is carry out and do what? Execute program instructions. That's all it can do. Then we have the makeup of the computer. Now this is a little different. What we did is this would be what we didn't, the name core didn't come up for a long time. This would be the actual processor. Carries out math and logic instructions. So the instructions they're either math or logic, or not. Then we can move stuff around. We call them data manipulation instructions. And then we started having so much graphics involved. You actually have a graphics section just to handle graphics. Instruction cache. Originally, so what the processor would do is the old processors, when you first came up, it would switch into what we call the fetch phase. And it would go out, and whatever it pulled in was going to be an instruction. And this would be a binary number. Then what it would do is it would switch to what we call execute phase. And it would do whatever the instruction told it to do. And then it would switch back into the what? Fetch, execute, fetch, execute, fetch, execute, fetch, execute. What they found out was this was very wasteful, that when it came into the execute phase, it might take 4 or 5 clock cycles to execute that instruction. And it wasn't doing anything during that time because everything was internal. So they said, what if we go ahead and while this guy's executing an instruction, why don't we just go ahead and prefetch information? So what it does now is that while it's executing these instructions, it'll go ahead and start loading additional information. So normally a program, and you're going to find this out in programming, normally a program goes down, and eventually what does it do? It loops. Or just about all programs just do this. Y'all learned that in robotics. So we'll have in robots, we'll have a program, we'll run, and then we loop. Our program automatically loops when it hits the end instruction. So what would happen, originally what it would do is, you'd start the processor, think about this, you got all these mailboxes out there, and every mailbox has got a different address. You'd go out there and you'd go to the next mailbox, it says, okay, go to mailbox 0, you go out there and take that mailbox, and you come all the way back into the house. And then you get back in there and you says, you look at the instruction that says, okay, you need the information from mailbox 1. So what would you do? You'd go all the way back out the house, do what? Get mailbox 1, come back in, look at it, and it says, okay, I need the information in mailbox 2. And this is the way the processors were originally written. So what they do now is they'll say, okay, we want to start with mailbox 1. There's probably a 99.9% chance that the next thing I need is in the next mailbox. So what they do now is it goes out to mailbox 0 and it grabs like 10 mailboxes, brings it in and puts all that in the cache. And then it does what? Then it says, does this one, run, it hits 10, and then it goes out to the mailboxes again and grabs what? Grabs 10. And it keeps doing that until finally it says loop. And as soon as it says loop, then it don't go outside anymore. Everything it needs is inside the cache. So this is why every time you start a program, it takes a little time, but once it's going, it's what? You ever notice that? So you start off with a dead program, it takes a little while to load it in, get it running, but once it's running, it screams. Because now we deal with these things called cache memories. So in the old days, it was fetch, execute, fetch, execute, fetch, execute. Now it's still that, but what does it do? It goes out and grabs a lot of memory and puts it in its caches. And they've learned that too. They do that on solid state drives. Solid state disk drives, if they use the technology that they're using, it takes a lot longer to write to it than it reads to it. But solid state drives are pretty fast because they run what? They run a big cache. So they know the information that you're getting probably comes from, straight sectors, right? You understand? So they'll go out and load it in the cache. So that's helped us with solid state drives. This cache memory is really, really neat. It's really, really increased the execution speed of our processor. Some of them have 3 levels. Most of them have at least 2 levels of cache, where you have level 1 getting it from level 2, but some of your processors actually have 3 levels of caches, and these processors really scream. Because it gives them the ability to go to a different program. It looks ahead and says, okay, the program is going to jump over here, and it'll go ahead and start prefetching information from over here before the program actually gets there. So these intuitive processors now are very, very smart. So this is the actual die of a i7 processor with Intel is still making. So this is the actual processor. These are the caches. Got 4 caches. I think this is what they did. I could show you our first file server that we had, and it literally ran 2 microprocessors. It's still over there. It's back when IBM went to the slotted processors instead of the socketed processors. But what they realized is integration, and so what they realized that integration was getting so small that they could actually take multiple processors and put them inside a single package, and we refer to those as cores. So now we got, I think the biggest one I know of is up to 8. But a core is a single processor, right? That's inside the same wafer. And if we have the right applications that take advantage of that, we call them multitasking applications. Then literally, the operating system can assign different tasks to different processors. So in the old days, when Microsoft Word originally came out, if you ran spell check, so you'd have the program and you didn't do it, and you'd have to run spell check, and then it would come out and check your program. But now spell check is running all the time because it's assigned to a what? It's assigned to a different core. So you got your application running over here, you got spell check running over here. So now spell check is instantaneous. So as soon as you type in a word on Microsoft Word, and if it's spelled wrong, what does it do? It turns red because it can assign that to a different. It can assign that task to a different core if the application is written right. So this is the Intel i7 block diagram. So here's the 4 cores. This is a quad-core processor. Then it's got a bus optic architecture. This is something you don't have to know, but this explains the difference between cores and stuff like that. So a 4-core processor has got 4 six processors inside a single way. But the program has got to be written correctly. We call a multitasking program that allows the programs to be split up into individual modules that can be assigned to different cores. We okay? Bus. How many conductors comprise an address bus? So a bus is a group of conductors that is shared by all the things. So we have the microprocessor has an address bus. This is used by the microprocessor to select something that it wants to communicate with. Everybody okay? It has what we call the data bus. The data bus is what it actually communicates with. So right now we're dealing with 64-bit processors. Which bus do you think that's defining? So this has probably got a 64-bit processor. Your computer's probably got a 64-bit processor. What bus are they defining? Then we got the control bus, by the way. This controls the communication between the selected device. So are they talking about the address bus, or are they talking about the data bus? If I could guess, that's the 50-50 chance. You're either right or wrong. I guess I'm going to start calling names. Huh? So, what determines how many letters the mail person can put inside a mailbox? The size of the mailbox, right? So the size of the mailbox would be similar to the data bus. So they're defining the data bus. So the data bus says, okay, this is how much data I can handle in one cycle. One cycle. So when they say it's a 64-bit processor that means there's 64 pins on that processor dedicated to the data bus. So they're not defining the address bus. The address bus determines how much memory that processor can address. So this guy here, I don't forget the size of the address bus, but it's well beyond what the application, what actually ends up determining how many addresses is the operating system that's running your computer. So when Windows XP came out, it could only address, I can't remember. Seems like it was 2 gigabytes worth of memory. The processor could address up to 16. Well, we'd have people that would go out and upgrade their computer. They'd get 8 gigabytes worth of memory in there, and it was a waste of money. Why? Because the operating system that operated the computer could only address up to 2 gigabytes. So actually, the operating system that's operating the computer determines how much memory you can address in there. So this is the basic makeup of a computer. We have the microprocessor, then we have memory, then we have input port, and then we have output this is representing big data. So if this was today's processor, this guy right here is 64 into the processor. Some microprocessors actually have a dedicated bus for memory too. So it'll have a dedicated data bus for everything else, and then it has a dedicated data bus for memory. The address bus is the control bus. So the address bus selects, the data bus is where the communication takes place, and the control bus controls communication. Luke talks about the address bus and talks about the data bus, but this bus right here is very, very important. So the analogy I use is a mailbox. So I got the microprocessor, right? I got an address bus. I got a 3-bit address bus. I got an 8-bit data bus. So what the microprocessor is doing is saying, okay, I want to get information from this address right here, which is address 4. All the devices look at the address bus. But only the one that's addressed, that's the only one that opens its door, right? Does that make sense? But then what do we have to do? We have to tell the device, what does the microprocessor need? Does it need information from that address, or does it need to put information in that address? So this is the function of a pin on the control bus. So right now it's saying, can y'all see what it says? It says I'm writing. So the processor would put out the information it wants to store. It'll put that on the data bus. Everything sees the data bus, but only one of them has their door open. Does that make sense? Then then it would take that and it would store it. So that basically would be one cycle. That would be what we call one bus. So the control bus tells it what to do with the data, or how to handle it, right? To understand. The address bus selects. And then the data bus is where that communication takes place. So this would be a read cycle. So now we're addressing address 6. All of them see the address bus. So it opens up its mailbox door. So it opens up the door. The control bus says, I'm reading. So everybody sees that, but only one is addressed. So what it does, it says, okay, the microprocessor is reading, so the mailbox puts the information on the data bus, and then the microprocessor reads the data bus. So that would be what we call a write cycle and a read cycle. So what did the address bus do? It's selected, right? What did the control bus do? The control. And what did the data bus do? This is where it actually communicates. So the data bus determines how much information it can transfer in one cycle. The address bus the size of the address bus would determine how many things it can select, and the size of the control bus would determine how much control it has. So right now we're only looking at read-write, but there's a lot more to the control bus than just that one thing. But a bus is just a group of wires that run out through the whole system, and then everything connects to it. Instruction. Instruction is a command given to a computer that specifies a specific task. So we're going to use symbols to represent instructions. So we're going to have output instructions, input instructions. Later on we'll have timer instructions, counter instructions. If you take some advanced PLC class, then we'll get into the instructions that the computer can do. An instruction set is a list of all the instructions supported by the CPU or programming application. So that's that little bar up there that I showed y'all, right? Where you could go through all the instruction set. That was all the instruction set for that process. Well, actually, it was in all the instructions supported by RS Logic 500, but the ones that wasn't supported by the CPU were grayed out, right? A peripheral, any device that communicates with the computer through a port. An An input port, a portal that allows information to flow into a computer. An output port, a portal that allows information to flow out of the computer. An input-output port, this is a portal that allows information to flow in and out of the computer. Note that generic term of input-output ports, they call it I/O, even though there's truly only one input and one output. So I can come up here and look at this computer. They don't show it as easy as they used to. But I'm going to come up here and I'm going to go to Control Panel. And I'm going to go to System Information. No, this is not it. This is Windows 7. There we go. So this is System Information. This literally shows the addresses where all these things are located. Now this is using a number system called hexadecimal, which we'll learn in a little bit before long. This is the size of the address. So the system timer is an address 48 decimal, system secret is all the time, this is address 61 of the so here's all the addresses that's supported. This is input output. This is not memory. This is all memory addresses. That's available. So this is memory. This is the actual binary address that your operating system uses to communicate with these different devices. Luckily, you don't have to know that, right? So this is controlled by your operating system. If I want to address my disk drive, it's at an address. If I want to address my video, it's at an address. If I want to do anything, it's actually got assigned a physical address. So this is called system information, that you can literally go out and look at the addresses that's assigned to this device. I don't know about Android machines. These would be available on any of the Windows operating systems. It's called system information, where you could actually go out and look at the addresses assigned to everything. Keyboards up here somewhere. So if you did machine language programming, you would have to know all this. You would have to know all the addresses inside the computer. But what we have is we have an operating system that knows all that, right? And this is one reason why you have Androids and you have Apples, because in Android systems, those things use different addresses than Windows systems, right? So that's one reason they're not compatible. So we have input ports, we have output ports. Inside the computer, there's some I/O ports, but generically, they're referred to as what? I/O. So we can look at these right here. So here's actually the state of these inputs. Now notice they're in groups of 16. And we'll talk about that in a little while. And this shows us the address. So this guy right here, let me do this so I can record that. This guy bit right here would be, this input right here would be addressed as I, then they put a what? Colon, 0. And then we'll talk about the dot. This is the big problem we have. This dot right here means something different in Allen Bradley and Siemens. And we can also look at output right here. So we start off output O, the letter O, not the number, and this gives us problems. Siemens realized this right off the bat, so somebody in this class is going to use a what? They're going to use an O for a 0, or they're going to use a 0 for an O, and they're going to have an error, and they're going to sit there and say, well, I can't see what's wrong with it. And you'll call me over there, and I say, well, you're using a 0, and it's supposed to be an O, or vice versa. What Siemens did is they changed output to Q. So if you look at your keyboard, the O and the 0 are what? They're by each other, right? So somebody in this class, even though this class is small, somebody in this class is going to use a 0 for an O, or they're going to use an O for a 0. Now, we used to slash our O's or our zeros or dash them. But now, the only difference is an O is rounder than a 0. So it's real hard to see when you're trying to figure out that. You'll have an error in your instruction. You're trying to figure it out. Hardware, the physical components of a computer. That's hardware. Software, programs or information stored in the computer's memory or peripheral that can be changed easily by the user. Usually the content stored in RAM or mass storage devices. Firmware, these are programs or information that is not easy for the end user to modify. Usually the content is stored in ROM. Originally, when we came out with computers, ROMs were fixed. That's all you had was ROMs. You could not change them. But since we came out with a memory called flash memory, a lot of times now you can actually change the firmware of your computer. We call that flashing, but it's not easy to do. So this computer right here, every once in a while, will you have to have a special application. Usually it's done by the computer maker, and you can't flash your ROMs easily, because if something happens while they're flashing, this is like your autonomous nervous system. So the ROMs in your computer is kind of like your autonomous nervous system. These are the things that you do without even thinking about it, right? Understand that? So this is the operating system that you're born with. So everybody's born with an operating system. So as soon as you're born, you can do certain things. What sort of things can you do when you're born? You can breathe. But you can't see real good. But it's there. It's not that you can't see, it's that your eyes are not fully developed yet. You can get rid of waste, right? So you can get rid of waste. Yeah. You got your nerves are already working with you, right? So you know you're hurt. So that's what we call the autonomous nervous system, and that's what basically the ROMs in the computer hold. It holds what happens when you born your computer. So every time you turn it on, right? Very seldom can we do that anymore. Most of our computers are always on a little bit, even though your phone, when you turn your phone off, yeah. Okay, guys, I noticed Corey got up. Let's take a break. By the way, about every hour we need to take a break, right? So what y'all need to do? Well, just do this. Don't say, do this, and then I'll get through with my thought, and then we'll take a break. So about 10 minutes.
So when you say ROM, you mean RAM, right?
No, ROM is not intended to be changed. So ROM is like your autonomous nervous system. It's what you have there all the time. Now you add stuff all the time, right? And we're a unique feature. We have the ability to upgrade our operating system. So like when you're born, you don't know how to walk. But you can literally program that into your autonomous nervous system. So after a while, you don't even think about it, right? So there's things that we can do. We're unique. The ROMs in a computer are basically, that's the autonomous nervous system. So if I come up here and unplug this thing, I pull the battery out and plug that sucker back in, and it boots, it goes into ROM. That's the autonomous nervous system. That gets the computer what? Started. It initializes all the programmable chips, all your inputs, all your outputs, gets them going. Eventually tells it to go out and load the main operating system from something, like a solid state drive or something like that. Now your phones, it's basically one thing, right? You understand? But yeah, so this computer, if I turn it off and unplug the battery, right? So it's not in standby anymore, it's truly what? It's truly off. When I plug it in, it's got to run programs. Those programs can't be in a memory that disappears when I turn power off. They got to be there all the time. So that's what ROMs are.
Okay. So another thing is that I was kind of like fiddling around with my laptop. I'm like, oh, how much RAM do I have? Oh, okay. And I started.
Well, you do. It depends. You know, if you don't do a lot of multitasking, which means you have 15 applications open at the same time, then what happens is that instead of all your programs being in memory, it does it'll keep some of them on your solid state drive, and then it'll start doing swapping, which means everybody else runs slow. So about the only time, so if your applications are running the speed you want them to run at, then upgrading the memory is not needed.
And some of the stuff that I do maybe run because
yeah, if you do a lot of multitasking,
like I'm on the go and I'm trying to like play a game or something like that, it's logged down.
Well, a lot of that too is
Graphics card.
Well, the graphics card and also your internet speed. If you're running over the internet, that kills a lot of people.
Most of my stuff though on laptop is usually like older games. Stuff that like my PC can run.
Yeah, I don't
15 times better than
I don't play games. Even though I built a couple of gaming computers.
oh, I got nice. I mean, I used to have this. My brother had bought a custom built one that the guy made, and I came in there, traded in one day, and he looked at it and he was like, "Hey, I'll give you a better one. Twice about 4 times better than this one, and I'll knock off $500. So it's like $10,000. I don't pay $500 for one that's vastly superior to my other one, all because he wanted that other one. He could turn around and sell it like I think he could do himself like 25 times.
Oh, really? That's what we used to do at the college. We built all our computers.
It's, if you've ever been down near Chelsea, it's the little computer shop next to the railroad track. That's really cool.
It's been a long time since I've been there.
But he's, what is it?
A little shop by the railroad track.
If you've ever, like, going towards, Chelsea City Hall, there's a railroad track there. Right next
Right down in town, right? Right through the track, turn right down through town.
Yeah, and right next to a, what they call a snow track, whatever. Chelsea, they got a bunch of crap there. But.
Isn't Chelsea on that? Is it on 25?
It's Chelsea's on today.
You ready? I'm going the wrong way.
He had one guy come in and request a specific style PC, and they had to custom build the plexiglass around it. The guy wanted I'm not doing it.
Well, that's the kind of stuff I don't put on computers.
Well, he's like, I want a solar theme PC. So
Okay.
they built a Star Tour type case for it with lights and everything.
Yeah, I don't. Yeah, my grandson, we got one. He's got lights on it that he can control with his cell phone.
I mean, my little like.
Yeah,
easy
that's-
from the 90s, but if you turn it, it's got a sheet of plexiglass in there. to get it.
I don't do that either.
But,
I don't care if anybody sees what I got or not. And I don't game anymore. I got too much other stuff too.
like,
Well, my grandson does, so we put him in our computer, and then my,
I mean, it's also nice, if you want to, like, get programs and stuff. Pretty good to do that too. I was trying to look into getting a new monitor though, because the monitor I have is 15 years old. And I'm trying to find a replacement for it, but they're so expensive. If
Yeah.
mine's able to run 4K, I want my PC and I want to get a 4K monitor. Whew. They ain't cheap.
like I say, I don't worry about that stuff anymore. Thank goodness.
They be expensive hobby.
It is. We used to teach all that stuff, how to build the computers, how to scope them out.
Yeah.
And we had a guy that was in the class, and he found a little computer shop that would give him credit. And him and his wife ended up getting divorced because he spent so much money on his computer that. So you got some people that just go.
They go overboard.
Oh yeah. It's just like the dang cell phone. That amazes me.
No. I mean, I had this phone for like 2 years, and my other one I had
Well, I had a 5S, and it finally died on me.
oh yeah,
And when I went down there, I said I want the smallest and the cheapest one you got.
and they give you to fix that.
Yeah. SX. I got an SX. I don't have it's an SX.
I'm 6S, and I'm like, all right.
No, mine's an SX. So it's not even. But it does what I wanted to do. I mean, good gracious, I don't.
Now, I will say this much, though. I'm not a fan of Apple for one reason.
That's all.
The part that kind of
That's all well, I don't know. I keep mine for years.
every other year, like, they don't think like you are. It's like, saying someone was smart about it, it's like, hey, you don't need this other headphone jack for the iPhone. Mine's just half. Well, I'll sit there, like, when I first got this phone, I had it for you. And my Bluetooth. Like, maybe a month later, my internet broke and my Bluetooth broke. So, I'm very fantastic. Never got the Bluetooth there, so eventually Wi-Fi started working. Oh, okay. But I'm never again like that.
That's all I get is Apple. They've been very good to me.
Nah, that's just, no. Like, don't fix what ain't broken. Or screen to break. I think like charge it $50 $30 for that master. Yeah, it's that. It's still charging more money.
Well, I don't buy Apple headphones. I just buy them off the internet.
No, I fixed
I just bought me a set. I think it's Toshiba. That's the noise canceling. That is so cool. So I wear it when I cut grass. You can't even hear my lawnmower. I play music on. So I just got the Toshiba. And they're really cool.
Now, I will say this. People have, several people who work on iPhones practice, and they found Samsung. Yeah. They can use Samsung parts, they can find. Finding an Apple. Yeah. I'm just saying, I mean, if you're looking at I don't know. I think it's like shot off really. It's coming off of it. It's like it's something, it's like a, I'm guessing it's supposed to be together or whatever. That no. Oh, that was one of your thoughts. But all that's going to do is make it go switch. I see that. What was the first thing that I want to see here today? Oh yeah, it's all fun and games until you hear that crunchy noise. Yeah, classic and everything. But you get mad at it. I don't know. I mean, you can fight it, but I was actually. Oh yeah.
So we have firmware. Firmware is programs or information that is not easy for the end user to change. Used to, you literally had to change the chipset if you wanted to upgrade your firmware. Since they came out with what they call double EEPROM, electrically erasable programmable read-only memory, we have the ability to change the contents of our firmware. But it's special. So usually when my Lenovo updates, they update the firmware. They tell me there's a new firmware update, and they do it. I can't upgrade the firmware. And they tell you right off the bat, make sure it's plugged in, and don't do anything while it's doing, because you're upgrading your. So the firmware is kind of like your autonomous nervous system, and this is what I was talking about. This is what you're born with. This is your operating system, your basic operating system. So this computer, if I turn it off, the battery fails, all that happens, and then I come up and I turn it on, it's got to have programs to run. And those are going to be in your firmware. All the information, like I said, it goes out there and initializes all the programmable chips inside your computer. So the only thing the processor knows is to go to a certain address. When you turn it on, it goes to a certain address looking for an instruction. And that instruction is going to be in your firmware. That makes sense? So that's the autonomous, we call it the BIOS. Have you ever heard that term? That's the basic input-output system of the computer. That's the basic one. And then as it goes along, it starts loading these operating systems like Windows and stuff like that allows you to get more control over your computer. Mass storage devices, these are read-write devices connected to an I/O port that allows us to save information. So used to, you'd say, how much memory you got in your computer? I got 5 terabytes. Well, what they were talking about their disk drives, right? You understand, not the memory in the computer. So this is just a place. So mass storage devices, computers use mass storage devices like we use books. What do we do with books? Or notebooks. So you're writing notes. That's a mass storage device, right? It's where we save information that we know we're probably going to forget and we'll use later on. Huh? Used to be. We have 2 processors. What we had is we had the instruction sets or the machine language instruction. I wish I could find some. We used to have a card that had all the instructions for the 6800 Motorola processor. But this is what we called a reduced instruction set computer and guys, I don't forget what this stands for. Let's see. It's an acronym. Reduced instruction set, Originally, the processors were sys processors, and excuse me for that, that's something I should know. I'm a published author on this stuff. So originally we had one instruction that did one task. So the instruction sets for these microprocessors were there we go. Complex instruction set computing. I knew that would come back to me sooner or later. So this is back when we had one instruction per task. So these complex, these sys processors was originally where they did it. What does sys stand for? So I remembered. It's a complex instruction set. Computer. This is actually the processor. Originally what they found, and this is not going to be on a test, by the way, because most of our processors right now are RISC processors, and this is where we have one instruction that can do multiple tasks. So as soon as they came out with that reduced the size of the instruction set and made programming a lot easier. So this stands for Reduced Instruction Set Computer. So the book talks about that, so that's not really important for us to understand. But we do need to know the difference between random access and read-only memory. Even though read-only memory is still there, so random access memory, we're going to have this. This is our read-write memory. So we have two types of memory. We have long-term memory. This is what we're adding to, by the way, to our firmware. And then we have what we call short-term memory. This is RAM. So what do we do with our short-term memory? We bring stuff in, we use it, we kick it out, and then we don't have no idea what goes on. Yeah. And this is RAM. So RAM means we load it in, we use it, then we do what? Then we kick it out. So right now I'm running PowerPoint. It's in RAM. As soon as I exit, it's what? It's gone. Right? Then I can load something else in there. I can load another application in there. So that's the RAM. So RAM, all computers have RAM. So when you write a program and you upload it into the you download it into the PLC, originally it goes into what? It goes into RAM. Read-only memory, this is what we used to have. This was our firmware. This was the programs that we never, ever wanted to change. But now most of them use what they call flash ROM. They're still called ROMs. They're intended for us to read only, right? And this is where your firmware is installed. But your computer or so right now, every once in a while, my Lenovo says there's a new firmware available for upgrade, and the company actually upgrades my firmware. And this happens on the PLC, so we can actually flash the ROMs on our PLC. But you got to be really careful with it. We had a problem last time. We were using the MicroLogic, the Compact Logic L24E, and we had two different versions of RS Logic 500. One of them didn't support that new PLC. The other one did. The problem is when they loaded that old one, it didn't support that PLC, and it told them they needed to flash the ROM. But it wouldn't work because the application was wrong, right? You understand? So, gotta be real careful with that. So one of the things you do on Allen Bradley, on the new Allen Bradley PLCs, you have the ability to flash the ROM yourself, but you have to run a what? You have to run a special program, right? You understand that? So now most of our computers has flash ROMs in them, which means they can be changed, but once they're changed, they turn into read-only. So you can't read-write to them. You can flash them, but once they're flashed, they're what? And this happens every once in a while on your cell phone. They'll flash the ROMs on your cell phone, and they'll tell you right off the bat to do what? Plug it into the charger, right? And don't use it. So your either Android phones are being flashed, they're flashing your firmware but you don't do it. Static. This is okay. Static RAM basically is, so we have two types of RAM that will run into a computer. It's kind of transparent in PLCs because we really don't know what type of RAM's in there. We just know there's some RAM in there. But there are actually two categories. There's static, random access memory. This stores it in little circuits called flip-flops. And as long as you don't turn power off, it holds that information. But these are what we call volatile memories. Volatile memories means if you turn the power off, everything that's in there is what? Gone. So if I come over here, I turn this computer off, I pull that battery out, anything that's in RAM is gone. It's volatile memory. So RAM is usually volatile memory. But it's short-term memory, so we can very easily do what? Load it back in. We have what we call DRAM. This is probably what's in your computer. This is a lot less expensive. This guy right here, transistor-wise, this guy right here took 6 transistors per storage cell. Storage cell would only hold 1 bit. This guy right here required 2. Technically it was 1. So that means for every one of the static cells I could put on my circuit card, I could do 3 to 6 of these. But the problem is that these guys kind of work like a battery. So what happens to the batteries? As soon as you plug them in, they start doing what? Discharging. Now, this is what's in your phone. So what do? You come back and do what? You charge them back up, right? You understand? So we charge up. So this is kind of like DRAM, but it discharges real fast. So DRAM occupies a lot less space, but you have to recharge it all the time. So all your ones, you have to go in and recharge them. We call this refresh. So dynamic memory has to be refreshed. This is done automatically, guys. We don't worry about it. We used to have what we call a dynamic memory controller, and you probably saw that. And its responsibility was to go out and constantly do what? Refresh that memory. So basically, it's transparent to it. So just about all the memory in your computer all the RAM in your computer is DRAM. I think we're on DDR4 now. So double data rate means they figured out a way to transfer information on. Used to we would clock the memory, so it's synchronous memory, and we would transfer only on the rising edge. Well, they figured out a way to make the memory transfer information not only on the rising edge but also on the fall edge. So that means automatically we could transfer information twice as fast, and that's what double data rate is, DDR. And then they figured out a bunch of stuff too. We run what we call 2 channels, where it addresses over in this set of chips, and then and then we can't access it over a little amount of time, or they'll switch over to another one. So they stagger the access, which really increases the speed of the thing too. But probably all the memory inside all the memory inside probably your cell phone, and all the memory inside your computer is DDR now, or dynamic. Used to we had all static memory, and those chips were big and eat up a lot of space. Data stored in RAM must be refreshed every few microseconds due to the discharge of the capacitor. So we have DDR, right? Data stored in SRAM remain unchanged until either new data is written or the existing data or power to be shipped. So your the cache inside the processor is SRAM. So that's not refreshed. Does not have to be refreshed, can be accessed faster than DRAM, usually used in today's computers as cache. Mask ROM. We don't run into this much anymore. Mask ROM, usually programmed by the manufacturer at the factory. Customer us order several thousand chips from the factories that we would cost today. So these are ROMs that still out there in computers. It means you can't, the only way you can change the contents of these ROMs is to change the chip. Programmable ROMs. Programmable ROMs are burned. We program them. And literally what they did is every storage cell consists of a little tiny fuse. And if we didn't blow the fuse, it would give us a 1. If we blew the fuse, if we blew the fuse, it would give us a 0. So we'd put this in a programmer, and we would literally send 1s and 0s in it, and it would pop fuses or not pop fuses. And, but these were one-shot, and it became known as burning. And we use that term right now, burn your ROMs. Even though it's flash ROMs, they'll call it burn. You'll hear people call it, you need to burn your ROMs, right? And you say, well, I'm not going to burn my ROMs or set it on fire. You'll run into that term too. So a PROM, we can program those. It's a one-shot deal. We can program them with a programmer. And I need to bring my program. We got a PROM programmer over there. We used to burn them. But it's terms burning, by the way. Erasable programmable ROM. It's usually in what we call a DIP. DIP stands for dual inline package. So it means we have pins down this side here. And I'll have to find these. These are really cool. These are still used, by the way. And then you can see it's got pins. It's in a rectangle. It's got pins on both sides, and they're in line with each other. So we call these guys dips. And then it's got a quartz window, which is glass right here. And then you can actually see the chip in here, and then you can see the wires coming off of it that would go over here to the different pins. And we got several of these. And what we could do on this is we could expose it to ultraviolet light, and it would erase it. And it was, our sun puts out a lot of ultraviolet light. You could put it outside, and probably would take about 2 or 3 days to erase it out there. So we had a high intensity ultraviolet light. It's basically kind of like a fluorescent tube, but it didn't have that guard, that mercury vapor guard up there to keep it from burning. And you could erase them, and then you could reprogram them in your programmer. So I could find some of these. And we got a microscope we can actually look in, and you can actually see the wafer. Used to, some of the guys would actually put little images and stuff on the wafer when they etched it to identify it as their chips, which is pretty cool. So these you can erase with high intensity ultraviolet light. But once you program them, it's firmware, right? They can. Then of course this has revolutionized our ROM right here. It's called electrically erasable programmable read-only memory. So we can erase EEPROMs with ultraviolet light. With double EEPROMs, we can erase those with electricity. So this gave us the ability now to have a non-volatile memory that we can electrically erase and reprogram. This is double EEPROM. So it's basically, it's not RAM, right? You understand? Because it holds its contents. RAM loses its contents if you remove power. The problem with this, it takes longer to erase it than it does to read from it. So you ever notice when you store stuff on this thing, it takes longer to store it than to get it off of it? Because it's literally got to do what? Erase, program. When you read it, it just reads it. This is revolutionized. Flash ROMs, this gives us flash ROMs so we can flash it. It gives us the ability to be able to carry a bunch of information around with us all the time that we can store information on and keep it, sort of like a disk drive. This is basically not done away with, but a lot of your laptops have moved to these for your mass storage. They call it solid state drives, SSDs. They're still very small, right? And they're fairly fast, but they're not. You're not going to go out and find a solid state drive. You can get 8 terabytes, right? So double E proms, this is revolutionized what we do. So we call them flash ROMs inside your computer. It gives us the ability to change the firmware in the machine. Well, we either have to have it, we either have to run a special application or the factory does it for us. So like your iPhone or your Android, it flashes it, it does what? It sends out a message saying you got an update, you need to, and they tell you to do it with your hooked up to a charger. And I hook mine up to my computer. On power up, the firmware stored in ROM carries out several instructions that checks the inputs, outputs, and other peripheral devices connected to the power. You can't see that. This is called a post. So as soon as I plug up this PLC, this is not going to be on mine. Lights up flashing, and all your PLCs that I've ever dealt with run through. That's it. Flashing, moving across. So what it's doing is just checking itself out to make sure it's operational. Now we refer to that as the post or the power on self-test. Every computer does that most of the time. Used to on the old ones, it would beep at you if it passed the post. Beep. Now they don't do that, unfortunately. So now you have problems. So used to, if it didn't pass the post, you could keep resetting it and see where it stopped at, and you could figure out where your problem was. But now our computers, when it runs the post, they don't let us know when it passes. You can usually see the keyboard lights flash when he's checking the keyboard. If you ever notice that, then they'll go off. That's when it's running the post. If you use an address decoder to enable ROM, RAM, and IO support and support chips. So these address decoders are taking that long address coming out of the address bus and decoding it over to something else. Does that make sense? So our IO, so I can select an IO, an input by using I, so that tells the processor that I'm using an input. Then we'll put a code. And then we're going to select a module number. So since ours are integrated right now, our modules are going to be 0 because they're inside the PLC. Does that make sense? And then I'll put a slash, and then I'll put a bit number. So this is the way we would address. Everybody okay? So what I just did is I addressed input 0, which is right around here. So that would be controlling whatever I'm assigning that input to. Now the actual address would be a binary address, which we don't see. What we see is we see it go to an address decoder that takes this information and selects the right input, right? So we can deal with an English language and deal with symbols when in real life everything inside the computer is in binary. The address decoder monitors the address bus and enables the address device to place data or read data from the data bus, and the control bus tells it what to do. Support chips, also called peripheral chips, also called support chips, used to enable the processor to communicate with input-output devices. Supports the NPU with different tabs. So this is something you all probably won't need to know in this class. This is when we hook up our inputs. And this is really important. And the book doesn't do a good job. I think it says one sentence somewhere later on. So what we do is we don't hook our inputs in series. We can, but normally what we do is we'll come over here and we'll have our PLC. And then our PLC will have input ports. And then, of course, this right here will be the program. And then sooner or later, we're going to generate an output. That makes sense? So ours has 10 inputs. What you'll find out real fast is that in computers, addresses start with 0. So 0 would be the first address. The analogy I use is in football, a lot of times the field goal kicker is 0. It doesn't mean they don't exist. It's an address. It's a number, right? So somehow what I've got to do is I've got to bring information into this port. Now we know a circuit requires two different things, right? It's got to have two different polarities. And then my input port would be over here. And then my input device, let's say I'm using a push button. I'm going to hook the push button to my input port. And we're using DC. So what's this over here? Is this a negative or a plus? Or is this a negative or a plus? We know we got to have different potentials. Well, technically, all we're trying to do is get information to flow into the port, right? You understand that? So we can come over here and make this a plus and make this a minus. Now this is inside the PLC. This is my port. This is what I have to do. I have to connect that over there. Or it might be configured where this right here is a minus and this right here is a plus. It would still give us 1 to 0. So we have two terms in the PLCs, and this came up through digital. So if you take digital, it'll make sense. But we got what we call sourcing, and we have what we call syncing. This defines what the PLC is looking for on the input. It's either looking for a minus or it's looking for a plus. So if I come over here, this is my actual input port, and I make this a minus, then this PLC is using a minus, so it would be syncing. So that means I would have to hook up what over, my input devices would have to do what? Source. Does that make sense? So that means what I would have to do, so I'm going to hook up a switch out here, and I'm going to hook it up to my input port. And I've got to hook something over to the left-hand side. So when I buy the PLC, or I configure the PLC, I'm going to configure it to either sync or source. Does that make sense? Most of the time, that's built in. That's something that you can specify. I want syncing inputs. Well, if you specify syncing inputs on your PLC, then that means the PLC is connected to the minus inside the PLC, and it's looking for a plus to come in off the device itself. Does this make sense? This is really important. So what I would have to do, so my battery, my power supply would be connected like this. Okay, and this would come into this side. This is internal, right? And then I would have to take the plus out, and I would have to run it out to my switch. So a syncing input port would require a sourcing input device. Does this make sense? Yes or no? This is really important because when you buy sensors, you're going to buy, so let's say you got a syncing, your PLCs are syncing, and you buy a syncing sensor. So manufacturers make the same sensor, either syncing or sourcing. And you buy the wrong sensor. You hook it up, it don't. So you got a bad sensor, you go out and buy a new one, you hook it up, it don't work, you take for granted it's what? Bad, or you think your PLC's bad now, because it's not, the PLC's not bad because you bought a syncing sensor when you needed a what? When you needed a sourcing sensor. Y'all understand that? Now push buttons don't care. Push buttons don't have a polarity, but solid state sensors, electronic sensors, are either going to be designed to sync or they're going to be designed to source. So you need to know that about your PLC. And when you hook up the power, you got to hook up the power right. Now this PLC, let's see if I can get this camera and zoom in a minute. stuff. So when I come up here and look at this, sorry. Okay. If I can get this close. Get close. Label, you know, see what this label? This is labeled DC com. So what we're doing with that four and six, and I can establish what I want the column to be. So if I put minus right there, it'll say the same. What happens? Five plus, right? So, or source, depending on the way you buy it. What advantages one have over the other? Actually, no advantage. So it's up to the company, what the company decides to do. And they're going to try to do all of them what? The same. And that way the electricians or the technicians, when they wire them up, they know how to hook them up. So what I'm going to do is I'm going to put the minus, so standard a lot of companies, most predominant source and output. So this, we'll talk a little bit about this. This guy has a relay output, so we can set a common for every output. Output zero, output one, output two. So I can literally configure or I can DC output. If I put DC output, then I got whether I'm setting it or most people have a little problem understanding that, and it gets them in trouble later on when they wire the PLC. So in this class, we're going to draw wires. And what I would do is I would just take that and just run it to where? And so our inputs would be, of course, we would have an input here. But let's say these are sensors. So sensors have a symbol, which are square, and then they have a diamond shape in the sensor. These are electronic sensors, by the way. And then, of course, I'll have push buttons. Now, the push, so is this parallel or is this series? Well, we can't say it's parallel because if it's parallel, we know one side's connected together, but the other side's not, so these are not parallel. But the way we program them in, so if this is input 0, 1, 2, 3, 4, I'm a 5, and then when I do my program, so when I do my program, it's the way we program them, right? So I come over here, so this would be my 2 rungs. Everybody okay? And then I would come over here and use this right here. And then I would say, I would want to address this. I'd say input, right? Everybody okay? Then I put a what? colon. And then I give a module number. Well, all our since the CPU does not occupy a slot, then all our modules are going to be 0. And then I put a slash, and then I define that bit right there, so I put a 0. Then I can come up here, and right next to it, I could hook this in series, and I could say input colon 0/1. You say, but they're not in parent series over there. But what we're doing is we're taking inputs and deciding how we're going to put them in a program, right? You understand? Yes or no? Then I could put what we call a down drop. We'll show you that. And then I could come down here and put this. And then I could assign this to say input 0/2. And then I could have come over here, and then I could assign that to an output. So we decide all the input devices are hooked up to input, and then we program them to be either in series or in parallel or whatever we need. Remember, how we hook up control devices does not determine if it's a series circuit or a parallel circuit. It's how we connect the loads, right? Everybody understand that? So syncing and sourcing, very important. Because when you go and buy these solid state sensors, push buttons don't care. They don't care if you put negative on the left or positive on the right or anything like that. Your input ports are going to require what you're going to give it, right? So if you run in syncing inputs, then your input devices have got the source. So syncing means negative, right? Sourcing means positive, and that's a term we use in PLC. They don't say you need to hook. You got to buy syncing inputs or sourcing outputs. So by default, on our PLCs, we use this, except for, so this would be our output port. So by default, we use sourcing, and then we run the plus out here. And then, of course, our output devices would be out here, except for the 1100s. The 1100s does this. What's that a symbol for? AC. So not the 1100s, the 1000s use AC. Syncing and sourcing has nothing to do with AC. Because technically AC has no what? Polarity. The only time syncing and sourcing comes into play when you're dealing with DC. Everybody okay? So y'all gotta let me know. If y'all have problems, don't feel, ask questions. Because I know this is not easy to understand. When you go to work for a company and you buy and you got a sensor, you got an electronic sensor that goes out, you have to determine, because that company is going to make them both syncing and sourcing. And if you buy the wrong one, it's going to give you problems, right? Won't hurt the sensor just won't work. So terminals, so we got to receive input. So this would be AC. So this would be like the inputs on the MicroLogic 1000. By the way, they're 120 volts. So when you get the MicroLogic 1000, where's it at? basically the same. I think it's got two commons on the top, and you can see they're jumped together. So this would be an AC input module, except it's a little wrong. We would have to have a resistor right here. So what this guy right here, this is a rectifier. What did I tell you rectifiers do? Converts AC into DC. You take solid state, you'll learn about that. Then this is what we call a zener. This is a voltage regulator. So what it might do is it might clip this and make it 24 volts, no matter what we get in. But you got to have a resistor in there. This is a light emitting diode. This is what we call an optical coupler, and this is what PLCs do. So what we want to do is we don't want to bring the input into all the electronics inside our computer, right? You understand? So we go through what we call an optical coupler. An optical coupler is built in. You can't see this, but what it does is it passes information through light. So when this thing lights up, it turns this guy here on. It's a transistor and allows information to come in the PLC. So that means if lightning strikes, it might wipe out one of your inputs, but it's not going to wipe out your PLC. That makes sense. So if you got extra inputs, you can move it over and change your programs, and you'll be okay. So all our inputs and all our outputs go through these optical couplers. And like I said, they're squares. They usually have 4 pins on them, and you can't actually see it. It's inside, but this is just isolation. It isolates the inputs from the inputs from the internals of the computer, and also it isolates the outputs from the internals of the computer. So this is typical input port, except for the resistor. This is a typical output port. So this would be DC. So this would be the PLC on this side. No, these are still inputs. This would be a DC input port. Ours is kind of like this, which means we can put DC or AC into them, right? Does that make sense? No, I'm sorry. We can put the minus or we can put the plus into it. So these are still inputs. These are inputs. They call them optical transceivers. We don't have to worry about that. But these optical isolators, these are designed to do what? Isolate the what? Inputs from the internals of the PLC. We don't care about Zener diodes. You'll learn about that. We don't care about optical latches. Triacs. These are electronic switches, but they switch AC. So we have 3 types of outputs. We have DC outputs, we have AC outputs, and then we have what we call relay outputs. So ours use relays. So on these right here and also on the 1100s, you can actually hear a click when you generate an output. Triac outputs would be solid state, but they would switch AC. Relays don't care what you put across them. So what we would have right here is we would have a relay coil. And then this right here would be a contact being controlled by the relay. So what's nice about, let's see if they show that. Yeah, here's relay. So a relay output, you turn on a relay coil, it closes the switch. But what can we do with a relay? We can either make it switch what? AC or DC. And it's going to be rated at a certain voltage. So I might be switching 120 volts AC, or I might be switching 24 volts DC. So the advantage of a relay output is one thing, you decide what you're going to do. So when we look at these PLCs, you'll notice that every output has its common. So you can have one output switching AC, you could have another output switching 120 volts DC, you could have another output switching whatever you want to. Now what you'll find out is that when you look at ours, we have them all looped together. So all the commons are looped together. So this is what I'm doing when I'm wiring them over there. And the first thing I do is see all the commas are just looped together. And then what I'm doing is I'm bringing plus DC into the first one. So we'll be using source and output, combine this to be source. But we don't have to do that on these PLCs, right? So what is that relay output have? You decide what's the disadvantage of a relay output. Seems like that would be the route to go, guys. So what would be the disadvantage of a relay output? First of all, it can't be as fast, because relays, you have to generate a magnetic field. The magnetic field has to close the contact. So they're not as fast as solid state outputs. So this guy here supports pulse width modulation, which is a method that we use to control DC motors. Even though this PLC supports it, I can't use it because the relays wouldn't switch wouldn't switch fast enough. Another thing, a relay is an electromechanical device. Your car is an electromechanical device. As soon as you say electromechanical, that means it can fail what? Two different ways. Your car can fail two different ways. It can fail what? Mechanically, or it can fail electronically, right? Or electrically. So that's the problem we have with relays. They do not, it's up to us. We can do whatever we need to switch with it. We can switch with it. But they're not going to switch as fast. They usually switch fast enough for normal operations, but these high-speed operations that are available now, I can't keep up with them. And also, eventually, something's going to happen to them. So that's our three different outputs. We have DC outputs, we have AC outputs, and relay outputs. Everybody understand the difference? DC is DC. DC, you're going to have to figure out syncing or sourcing, right? You understand? AC, we don't care. AC has no polarity. But AC, these guys use triacs, and they're extremely fast, but they're going to be AC. You can't change it. And in relay, you decide what type of current you're going to use on that. So every one of them's got their features. So all our PLCs, except for the 24 L, they have DC output, so they don't have relay output. But the 1000s and 1100s both have relay output. So if we bring analog in, we got to have an analog to digital converter. So we're going to learn a little bit about number systems, guys. So we know we got a single digit. Anybody know what we call a single digit of a binary? It's referred to as a bit, right? And then we can start dealing with numbers. And we have a group of 4 that we refer to as a nibble. You can't find that very often. And then we have a group of 8, but this would be a number now. So that number right there has weight. So that's more than 8 bits. Anybody know what we call a group of 8 bits? Yeah, we call it a byte. So this right here, in decimal, this would equal, if I was to take this and convert it over to decimal, that would be the number 5. So come over here and do this. Then that'd be what we call a byte. I think that would be equal to 136 in decimal. Don't hold me up on that. And then above this, we have a group of 16 bits. This is going to vary from computers, but in computers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We refer to this in computers, we refer to this as a word. here's where it's gonna change, and I'll give y'all what we call it, then we have what we call a double word. So what would a double word be? So if a word is 16 bits, what would a double word be? 2 times 16, 32. So a double word would be 32 bits. Then we have what we call a quad word, which would be 128 bits, and it moves on. Basically, in computers, words is, microprocessors, words is but I'll give y'all the terms on those. So what we do is we take an analog input that might be, let's say, 3 volts. It comes into the A to D converter, and then it would convert it into a binary number that represents that. So that would be a 3. That makes sense? And then it's up to your computer to figure out. So that's what, so an analog to digital converter takes an analog and converts it over to a binary number inside your computer. A digital analog converter, we would give it a number like 3. And then the digital analog converter would output like 3 volts. That makes sense? So to understand A to D and D to A converters, we're going to have to understand how to convert between these numbering systems a little bit, guys. So that's one of the things that we're going to deal with in our next lecture, I think. Program language controllers are used to implement specific instructions. Input-output instructions, we're going to use a lot this semester. Timing down. Installation will get to those ILC 196. So supporting arithmetic will get into those. We get to ILC 196. Logic will go to those. ILC 196. Just say, education, this is where we really like. We just don't have time. We'll get into that a little bit and take set up a Ethernet network. Are we okay? What time is it? Oh, yeah, it's about time. So this is where we'll continue on. We'll come back in the second class. So this class ends at like 11:50.
Yes.
So computer languages. So this is the languages of the program. Programmers, source code, drivers, instructions, and then these languages right here. Luckily, this is the language we program. We'll call a high-level language. This is the only language that's a processor. A lot today. I know y'all hate these long lecture days, but we got to get a lot of stuff out of the way before we let y'all start playing around with these guys, right? Even though I know y'all want to. Yeah. You mean that powers chart? It's on the website. So you already had digital. I might let you teach the class. So you've already had all the numbers sisters. So I'll let y'all run a program that I wrote. This was written in Visual Basic, by the way. We'll have a lab where you do that. I think it might still be running in the background. I'm not sure. No, I don't see it. All right, guys. See y'all on Thursday. No, this is the last. See y'all next Monday.
Yeah. So we'll see you Monday.
See me Monday.